Welcome. My name is Lukina, and on behalf of my co-authors Christian Schilling and Thomas Henzinger, I'm going to be your guide today on this journey into the unknown, active monitoring of neural networks. Let's look at the typical learning pipeline. We have training data. We have some pre-processing that happens to this data to make it clean and prepare for the training. And then we have model development itself, where a learning algorithm processes the data and produces some output, such as classification. Then this output is given to an autonomous system, for example, which is directly deployed in the environment, and it can be also a hostile environment. It can be an environment full of unpredictable behaviors, which were not taken into account during training. So where exactly in this process can we intervene to maybe make sure that this model that we use already at the deployment actually is verified, or to make sure that the data is processed correctly, or maybe the outputs adhere to what we expect to get from a model like this. So of course we can check the input of the neural network or some other model that we have in mind. So the neural network here is just for presentation. We can, of course, also look at the layers of the neural network and see maybe the behavior in the layers is already suspicious for us. And we can make sure that the output is robust enough to various things that the neural network can see in the real world. But then also, don't we need to look at the deployment stage? And this stage is the most vulnerable one, because when the neural network is already deployed inside an autonomous system or a safety critical system, like for example, an autonomous car, we need to make sure that it performs exactly the way we expect. And if this is not the case, we need to maybe adapt the neural network to the behavior that we expect it to have. So we know that there are approaches that look at the input of the neural network. There have been already approaches developed to look at the inner layers of the neural network and look at the behavior that the neural network learned during training to make sure that this behavior is exactly what we need. And of course, to make sure that the output is correct. But we unfortunately still require algorithms that are still lacking in the state of the art that monitor the neural network when it's already deployed in the real system, in the real world. Not only monitor, but also quantify the behavior of the deployed neural network, communicate it to a human authority or a supervisor that can provide feedback. Why this feedback is so important for us? Because we would like to also adapt to the behavior that we see in the real world. This adaptation is the most crucial stage. Why? Because if the neural network doesn't behave the way we want, we need to make sure that at least some behavior is safe until the neural network is retrained or incrementally trained to adjust to the novel inputs. So this is already a lot of things that we need to do when the neural network is deployed in the real world. And let's unpack what's happening here. So first of all, how a common neural network reacts to novel input classes. So let's look at this one here, which looks very simple. We have an input layer, we have some output layer. And let's say this is very schematical representation of a simple neural network that learned to differentiate between two traffic signs. This is an icy road and cars prohibited in the area, if I'm not mistaken. So let's say that this neural network is very good at this kind of predictions. Now, what happens if this neural network sees completely new traffic sign? Well, it tries to somehow maybe match it with its knowledge, match it with something that it already knows and trained before. So this is kind of a triangular shape. So maybe this is this sign. Maybe this is I0, the neural network assumes. Well, what happens is that the neural network in this case is highly likely to predict the output with high confidence, which is wrong. While in fact, what it should have done instead is to inform us that it doesn't know or not sure about this input and not sure about the prediction of this input. So this is the desired behavior. Unfortunately, we do not yet have this behavior. And therefore, there were approaches that also us introduced in previous work that address this novelty monitoring. And what we mean by that is that when novel inputs enter the neural network, and the neural network is trying to predict what these inputs, what kind of classification these inputs should have, we monitor what's happening inside the layers. And we try to warn the observer or the user if the neural network is not sure about the prediction. And maybe the input has a completely novel class that it has never seen during training. For novelty detection or this kind of situations for neural networks, there are approaches that exist both in formal methods and machine learning. In formal methods, we analyze neural valuations, meaning we analyze the inner layers of the neural network. In machine learning, usually what's analyzed typically is the input distribution of the data that the neural network processes. Both approaches in both areas are quite domain specific. So for a specific data set, there are specific approaches that work exactly with this data set. And what's the biggest difference between machine learning and formal methods when addressing novelty detection is that machine learning tries to prioritize the accuracy of the prediction. So the novelties are addressed such that we minimize the loss of prediction accuracy. While in formal methods, we're focused on safety. So for us, each novelty is crucial. And of course, in machine learning, there are already approaches that can also adapt to novel behavior when it's detected. In formal methods, however, such approaches are still lacking. Why? Because formal methods do not really scale well for adapting the neural network at runtime. In previous work, we developed an approach that addresses novelty detection for a neural network using very simple abstractions. These abstractions are based on interval representation of neural valuations. How exactly does it work? So let's say we have this neural network again. Again, it's a simple neural network, and in principle, we don't even care what kind of traffic signs they are. So let's assume that these are just orange squares and orange and green. This is what neural network learned to identify. And what we are going to do is that what we did in that work is that we look inside the last layer or several last layers of the neural network before the prediction layer, before it makes its prediction. And we build an abstraction based on all the training data set that we have of the behavior inside these layers. So for each input from the training data set, we would make a point here on the space of all the neurons inside the layers and color it according to its classification in the training data set. And this way, we obtain this kind of interval abstractions that we called boxes or box abstraction that we can later use to monitor if something novel appeared in the input. So we noticed that these box abstractions are the cheapest ones and also the most effective ones. So what happens when some novel input of the class that the neural network has never seen before enters the neural network, we can easily see if this input is outside the abstraction that we learned from the training dataset, which means that the neural network has never trained to identify this input, and maybe we should take care of it. So why it's boxes? Like I said, it's computationally very cheap. It's very cheap to compute, and it's also very cheap to monitor if something is inside or outside the box. It proved to be effective in detecting novelties. It is independent of what kind of data set we have and what model of the neural network we have, as long as we have access to the inner layers of the neural network. It is easy to integrate into other novelty detection approaches and combine maybe with approaches from machine learning. And it is flexible to the user configuration, which means that the user can also say whether they want to see more false positives or less false positives and other parameters. So now, this work that I'm presenting today, we call it active monitoring. Why is it active? Because when the neural network is already deployed, the novelties might be coming in very frequently. And it is not enough to just use a static monitor that detects novelties. Why? Because we need to identify what's novel and what's novel that we already know. So let me show you how we do it. So let's say this neural network still learned only for 2 classes. And now this new class of inputs came in. We labeled more samples of these inputs and gave it to the neural network and completely retrained it from scratch to now also classify these novel input classes. So now the neural network knows 3 classes. Okay, that's good. But now there is a new traffic sign. And what happens? The neural network misclassifies this traffic sign again. So what we have to do? Well, we have to do the same procedure. We have to take the neural network, give it more training data, and retrain it completely from scratch, such that it knows now 4 classes. And now another traffic sign comes in. For us, we clearly see that this traffic sign is very different, but for the neural network, it might not be. And then we have to do this expensive procedure again and again. And if this kind of novel classes of inputs come in very frequently, this becomes very costly for us, especially when the neural network is already deployed. So what we propose is active monitoring framework, which we present here today. We have training data, training input, and we process this training data and train a neural network that differentiates between desired classes of inputs. And then we deploy it, and at runtime, this neural network receives runtime input. So now we propose to attach a quantitative monitor to this neural network, to this process. Why it is quantitative? Because it doesn't only detect the novelties, but it also computes various metrics about these novelties. So it computes, for example, how far the novelty is from the classes that the neural network already knows. This information is very important for us as an observer or a human authority. Then the novelty, if it's far away from everything that the neural network has known so far, is given to us or the human observer. And it is for us to decide whether this is a new class of inputs or whether everything was correct. So if it has been a new class of inputs, or if the monitor was wrong, we need to do an adaptation stage. During this adaptation stage, not only we incrementally retrain another neural network model that will help us with future detections of the novelties, but we also adapt the monitor itself. So the monitor will now include also the knowledge about these novel inputs that accumulates while the neural network is deployed. So this is in how the framework that we propose. Let me show you the example of a metric that we use to identify whether the novelty is novel enough, so to say. For example, this is the distance metric that we noticed performs the best for our approach. But of course, other metrics can be introduced and easily integrated into this framework. So in this case, let's say that we look at principal components of the neural evaluations for two classes. This is orange class and blue class. So let's say that we look at the points in here. So this is our point now. What we would like to compute first. First, we would like to compute the distance, or so-called box distance. So the distance metric from this point to the blue class. So we compute the distance metric from this point to the blue class. And we do it for each cluster in our neural evaluations. So then we find the closest cluster, and this will be a distance to the blue class. We do the same for the orange class. So we compute the distance to all the orange clusters. And then we take the one which is the closest. So this minimum distance will be the distance to the orange class. And then we can say to which class, orange or the blue, this point is the closest. And if neither, then we say that this point is completely null and it doesn't fit to any of the classes. Otherwise, we can even maybe provide a suggestion to the authority that maybe it should have been in an orange class, but we are not sure, so maybe you should check. But as I said, these novelties accumulate over time. And there's a lot of them that can come in undetected. And we must differentiate between different classes of such novelties. And therefore, we need to incrementally train another neural network model that would also help us identify whether something is novel compared to the novelties that we have already seen. And this adaptation happens with first asking the authority what the label of a novelty should be. And then either the authority tells us that, well, the neural network was actually correct, and then we need to adapt our monitor, or the neural network was wrong, and we need to collect enough samples and adapt the model itself. So this is the adaptation stage. And here, just to show you an example that this approach, this framework of active monitoring that we propose performs better in terms of the precision of the monitor. And we can see that here, so our quantitative monitor is in blue, and it manages to maintain high precision in detecting novelties over time due to the adaptation stage, while other monitors start deteriorating in precision as more and more novel inputs come in. And of course, there are various cases how this behaves on different benchmarks. But we also noticed that due to the adaptation, we ask the authority less about the labels for the new incoming inputs. So this is, in short, what our framework is about. And just very quickly, what we would like to do with it. So we all know that automated or autonomy means that there is some algorithmic part, software in the system implemented and deployed. And there are various stages of autonomy that have been identified. It can be assistance systems, when the operator is assisted by the automated system, but remains in full control and can intervene anytime. Or partial autonomy, when the operator must monitor the system, and prepared to be intervening. However, transitioning from one level to another between these two levels is already a quite challenging task, and there is a big gap between them. So we claim that this requires active monitoring and adaptation of the monitors. So transitioning, for example, from level 3 and 4 with your favorite AI algorithm or a neural network training requires an intervention of a human authority. But how? Well, our framework allows to do so. So it allows you to monitor the behavior inside the layers of the neural network and communicate with the human authority for feedback. And this feedback is quite valuable for you to adapt to the novel behavior. And in the future, we would like to also look how this framework can help us do safe exploration, for example, in reinforcement learning, or to adapt learned controllers at runtime. And if you are interested in our work, we will be more than happy if you look at our open source repository and give us your feedback. Thank you very much for listening.